Okay, so this video is going to talk about another dissection. So this is from Proposition 24.4 in your textbook, and it starts off, the assumption is we're in a Hilbert plane with Playfair's axiom holding. We're going to be given some rectangle ABCD and a line segment. And here's what we know about that line segment. We know that it's longer than side AB of our rectangle, but it's not as long as twice the length of that side AB. Then what we want to do is, the claim is we can go ahead and dissect the rectangle ABCD into another rectangle, but here's the deal, that second rectangle has to have one side that is or is congruent to AE. Now, when you're doing dissections, it is a best practice to try to have the second figure on top of the first figure if you're creating your own second figure. Why? Because overlapping parts are automatically congruent to each other. Save yourself some less work. So if we go about this, let's start off and deal with our scratch work. So step one is dealing with that scratch work. So what we'll say is, all right, suppose we have some triangle ABCD. My really, really terrible rectangle. Okay, so suppose A and B are here at the bottom. Suppose C and D are up here at the top, C being the pretend point that had an issue when my hand shook there, and AE. I like to go ahead and put AE down here at the bottom. Why? Because as soon as you extend that guy at all, if you have here A, B, C, where B is between A and C, you automatically have, by the definition of inequality of line segments, that AE is longer than AB. Now, if you want to guarantee that AE is shorter than double the length of AB, just make sure you stop before you have a second copy of AB over here. So suppose we have something like C maybe right about there. And that's it. Okay? So, wow, don't do actual C. Do E. E. I was getting too happy with C. Sorry about that. All right, so now we've got what's given. Now, we want to have a rectangle that is equivalent by dissection or has the same area as ABC, but one of the sides is AE. So what do we know? We know that we can now share a side here. We go up somewhere from A along C. I don't know how far up. And we're also going to go straight up from E. And I'm totally eyeballing this. Maybe it's something like that. Okay, so I'm going to go ahead and label these points. Maybe this is G. Maybe this is H. Let's call that intersection L because we'll need it in the future. Okay, I'm not going to guarantee by any way, shape, or form that that's a great picture because it's totally freehand. Okay. Now, turns out in order to get these two guys equivalent by dissection, what do we need? Well, the original rectangle is this guy. I can't say it's a square, but it's definitely a quadrilateral, so some sort of rectangle. That's the overlap, so that part definitely is congruent between the two figures. And then you need to figure out if those two guys are. Now, there's no guarantee that they're congruent, so you need to cut it up into some pieces. So here's the trick. The trick is actually to draw in a line that you might not expect. You draw on the line E to C. And this is why I was a little unhappy about C being so horrible up there. Okay? So what we're going to do is the following. We're actually going to cut these two figures up into the following pieces. We're going to cut rectangle ABC up into the piece. The weird pentagon shape, so let's put in these letters so we can actually deal with this. Maybe we call this guy K. Maybe we call this guy F. Okay? So we've got a triangle. Triangle CGK. We've got another triangle. Triangle CDF. And then we've got that pentagon. So this is A, B, F, K, and G. Okay. Now, if we then look at the other rectangle, and the other rectangle would be A, E, H, G. This guy, and I want to put pieces here that are going to be congruent underneath. So for the second rectangle, we also share that same pentagon shape. So A, B, F, K, G. These guys are going to be equal to each other, so if they're definitely congruent. Now, for the tiny triangle, we want that one to be congruent to the tiny triangle down here. So that one is supposed to be congruent to F, FBE. And then the big triangle CDF is supposed to be congruent to this guy. So I'm not going to lie, I think of CDF as sliding down in terms of how it's moved, and then we pick this guy up and place it in the hole. Okay? So CDF is supposed to be congruent to KHE. Okay? So those are the two that we're actually going to have to prove are congruent to each other. So if we look at them, we notice a couple of things. One of the things is if we actually have rectangles, we're going to have a whole bunch of right angles and a whole bunch of parallel lines. So the angle at B and G would be a right angle. We would also have that the lines EH and A to C would be parallel. And if those guys are parallel, well, we get a bunch of different things. One of the things that we get is, well, we actually don't care about that one. What we need is this one. Well, that's given, these two lines being parallel, AC and BD, because we started with a rectangle. So those two angles would be congruent immediately. And then we say, all right, well, we could, of course, figure out that the third angle is congruent. If you wanted to, you totally could. But we need to have one of the sides to be congruent because otherwise we'll get similar triangles but not congruent triangles. Well, with the hypotenuse here, we just don't have enough information to show that they're congruent. This here, again, not enough information to show that they're congruent, but point G here is actually somebody we're going to have to get in terms of when we're actually constructing that second rectangle. So we better have some information about G. So here's what we'd want. We'd want that line segment CG and BF to be congruent. So if we look at these guys, if we look at triangle CGK and we want this thing to be congruent to triangle FBE, automatically we're getting that angle G congruent to angle, where'd it go, B. I'm going to be lazy and put B right here. And that's due to them being right angles. We're also automatically, well, not really automatically, but angle C. So GCK congruent to the angle there at F. So that's angle BFE. And that is corresponding angles. That's in the same proposition in Euclid's book 1 that alternate interior angles is in. He's got corresponding angles, alternate interior angles, alternate exterior angles. And then the thing that we need, and here's the big starred thing that we're going to force to have happen, we need that CG congruent to FB. And if all of that happens, these two guys will be congruent by way of angle side angle. Okay. Now, the other guy that we need to be congruent is triangles. Where'd it go? CDF. There's the big one. Congruent to triangle KHE. That's the other big one. Now, a couple of things that we'll know off the bat if we have rectangles. Angle D and H are right angles. So here's angle D congruent to angle H because they're right angles. We'll also get, and it's up to you which ones you want to do. You could either focus in on angle C and K, or you could focus in on F and E. It's going to be the same reasoning, but if you look here at angle C marked, angle K marked, those guys are going to be congruent to each other. So this is angle DCF is congruent. Wow, that has too many letters in that angle's name. Just a second. DCF is congruent to angle HKE. And that is, again, corresponding angles. And the last thing that we're going to need is I'm actually going to claim here that the side CF is congruent to the side KE. Well, I lie a little bit. That's one of the things that we're going to need. So I'm going to star it. Okay. So this one up here we starred and we said that one was going to be true by construction. It turns out the second one not going to be, well, I mean, once we construct the thing, it'll be true. But it's not just by way of us forcing it in the construction. This one is actually adding angles. So this one goes as follows. I'm going to claim that CK is actually congruent to FE. Now notice where CK and FE are. These are the hypotenuses of the two little triangles. So these guys will totally happen once you have the first little triangles congruent to each other. So notice order here matters. We're going to have to do the little triangles first and then the bigger triangles. Now once we have that, we'll go ahead and add in this shared bit of the line segment K to F to get the two longer guys. So this is where we're going to add angles. So that'll be the key thing there. So notice in terms of a game plan, we've totally mapped out what we need in the picture. We've also mapped out how we're going to do our proof. And in terms of the construction, the only big thing we're going to need is we're going to put in this line CE, that's the trick, and we're going to go ahead and make this point G to be exactly the same length as F to B right down here. Once we know where point G is, we can totally drop this line that's perpendicular to AC, or if you prefer, parallel to AB. Same deal with this line HE, either perpendicular to AE at E, or parallel to AC through the point E. You can do it either way, it doesn't matter. I'm actually going to do it the way with perpendiculars, how I got it prepped up. So, next step, we're going to go into the construction. So for our construction, I'm going to go ahead and actually do a construction here and break out the proof in the next slide. So we're given the original triangle ABCD. We're then told we have the line AE. I went ahead and drew it in here, and notice BE right here is not yet a copy of AB. Visibly, I on purpose made it so it looks shorter. That way you believe it when we say, hey, line segment AE is longer than AB. Obvious from the picture, and shorter than 2 times AB. So first thing we're going to do is we're actually going to form that line CE. There's our trick. That allows us to get our point F, which we're then going to use. We'll copy our line BF, that's right there, up to CG. Notice I dropped it below C. This allows us to get that point G. Now remember where G was. G was going to give us the other side of our rectangle. So we go ahead and we say, let's drop a line that's perpendicular to AC through the point G. Bam. And then we're going to go ahead and drop a line that's perpendicular to AE through the point E. And in practice, you would just let them intersect where they intersect. Since I did this computer generated, I already knew where that point H was going to be. Okay. Now, at this point, we have a rectangle that is supposedly equivalent by way of dissection of the original rectangle. And notice, because the original rectangle here was skinnier and taller than the one in our sketchwork, these guys look a little different. Okay, but same gist. Okay. Now, in terms of the actual formal Hilbert construction, that's literally it. You've got the rectangle that you're going to want. Now, the rest of the proof by dissection is actually showing that all the pieces and parts work, namely that this little triangle CG unnamed point is congruent to FBE, and that this big triangle of CDF is congruent to the triangle HE2, again, unnamed point, and then this pentagon is shared between the two, so no worries there. Alright, so let's do the last step, which is the proof. So I have the same exact picture, the only thing I pulled off here was point F. I have the same exact construction steps here, so you can always put the construction and the proof together. That's actually a really common thing to do. I've been splitting it just because we split it back in classical geometry too. Okay. So I'm going to insert a step 3 here, and that insertion of step 3 tells us that point F exists. It turns out F exists here. Well, you could actually do it a couple different ways, but plane separation is one of them. Here, notice the line BD. E is on one side of that line. C here is going to be on the other side of that line. So what do we have? We know that F has to exist because you cross over the line. Could you do it other ways? Sure, but that was the way I thought of. Then we have the rest of the construction. Now, just by the way that we dropped all of these perpendicular lines, we're automatically going to get a bunch of right angles. The angle at A, both the angles at B here, the angle at ACD, so the big one in D, all of these are automatically right angles, and that's just the definition of a rectangle right there. A rectangle says you have 4 right angles, nothing else. Okay. Now, the angle at G, so this guy right here, and the angle at A EH, so there and there, are also right angles, and that's the definition of a right angle because we dropped two perpendicular lines. Remember, right angles and perpendicular lines are all part of the same definition. Okay. Notice what this means in terms of what we've got. We've almost got every single right angle possible listed out. Turns out we also can say the angle at H is a right angle, which was the only one we'd missed before. Please tell me that was the only one we missed before. 4, 5, 6, 7. Excellent, only one we'd missed before. And this one actually is a right angle by a different reason. This guy's right by way of Proposition 1, Book 1, Proposition 34 in Euclid's Elements. We have this one because we have Playfair's axiom, but what it says is opposite angles are congruent. So if you got a right angle, you got another right angle, is one way to say. Notice what this also tells you by getting these 4 right angles. This also automatically gives you that this guy's a rectangle. Bam. And let's go ahead and throw in the points that we were talking about when we did scratch work. K and F also exist, and you can use the same logic as what we did for point F existing, namely plane separation. We're actually not going to need L. Double check. I don't think we're going to need L, but I threw it in there just because we did it before. All right, so this here really gets you all the nitty-gritties, all those things that you were basically assuming. Now let's get into the actual showing the different triangles are congruent. All right, so I just left the main things. We've got 2 rectangles, and BF here and CG are congruent to each other. So first thing is, remember how we talked about parallel lines quite a bit when we were dealing with our angles, when we outlined how to show that our triangles were congruent, namely we had corresponding angles? Well, you can only have that if you have parallel lines. So my claim here is we got a bunch of parallel lines, and it turns out there's a proposition about the middle of Euclid's Book 1, which we totally have just by being in a Hilbert plane, that says, hey, depending how your angles are all oriented, and we've got a bunch of right angles here, so that works. Depending how your angles are oriented, you got a bunch of parallel lines. Okay, so I just went ahead and did all of them, those 3 parallel, and then those 3 parallel. All right, so next guy is if we look at our 2 teeny tiny triangles, and remember we said we had to look at these guys first to show they were congruent first. My claim here is the angle at C and the angle at F are congruent, and the reason for that is corresponding angles. Okay, or corresponding angles, alternate interior and alternate exterior angles are all in Euclid in Proposition 29, Book 1. Again, we only have that because we have Playfair's axiom, holding it in the Hilbert plane. So we've got one angle established. We already have all of the right angles established, and we actually have the side of CG and FB being established as well. So what I went ahead here and did is, technically speaking, we only talked about the right angles as right angles, but we know right angles are always congruent to each other, which is what Proposition 9.6 tells us. Okay. So that tells us, using angle, side, angle, that we totally have 2 triangles that are congruent to each other. Now, immediate result of that is we're going to have our 2 sides, namely the hypotenuses, congruent to each other. So we're going to use that, remember, when we were looking at whether the 2 larger triangles are congruent to each other. Okay. So now we're transitioning into that section. So my claim is that CF, so C all the way to F, and E all the way to K are going to be congruent to each other. Proposition 8.2 says you get to add line segments. Namely, it says this in our context. CK plus KF is congruent to FE. That was trying to be an F. That F is not working out well. So let's start over. FE plus KF. And technically, it looks like I missed something. And the thing I missed, if you guys noticed it, was KF congruent to KF. And this would have been by C2. So this guy. Now, what does that give you? That gives you the hypotenuses of your 2 big right triangles are congruent to each other. Now, what else do we know? Well, we know that we had two right angles at D and F, so we know they're going to be congruent to each other. And we can also look at the angles at C and the angle at K, and those two guys are going to be corresponding angles off of those parallel lines and the transversal CK. Okay? So this is corresponding angles again. Angles. Which means we have what? We have two angles and one side that are congruent. So we totally have that the two big triangles are congruent to each other. This time angle, angle, side, because the side was not between the two angles. Bam, done. Now, let's put all this together. So, what do we have? We know that from our diagram, in terms of our dissection here, or our potential dissection, ABC could be divided up into CGK, the big triangle CDF, and the pentagon ABFKG. The other rectangle, AEGH, could be divided into small triangle FBE, the big triangle KHE, and that same pentagon. Those two automatically congruent. We just had to show those two pairs, and we did. That one we did first by angle, side, angle. And I don't think we did angle, side, angle, did we? Which ones did we do? Yeah, we did angle, side, angle. Okay. And then the second one we just did, which was by angle, angle, side, because the side was not between the two angles. And automatically, if you're overlapping in the same figure, those two are equals. So what does this tell you? If we've matched all three of our pieces and parts, this tells us, hey, the original rectangle ABCD, by using this dissection, can be dissected into the other rectangle AEGH. Now, is there another way to do that? Could you divide it up into different pieces? Sure. Is there a different rectangle? Only if you move the side AE to somewhere else. But that would be how you dissect a rectangle into another rectangle.